We are talking about transformer basics and we have seen two questions. Actually, there is a mistake while solving this question. So that's why I'm retaking this question again. Okay. Gate 92 question. So what question says two transformers of same type using same grade of iron and material are designed to work at same flux and current densities, but linear dimensions of one transformer are two times that of the other in all respects. Now they're asking us to find out the ratio of kVA of two transformers closely equals to. So for a transformer generally, the kVA is proportional to the induced EMF into current. And generally current expression is given by equal to J into A. J is a current density, area is a cross section of the current. Okay. So here I can write I2 by I1 equal to A2 by A1. Since current density is same because we are using the same material. Whereas they have mentioned that the linear dimensions of one are two times that of the other. So therefore A2 becomes 4 times A1 by A1. So I2 by A1 equal to 4. Now we know that induced EMF in a transformer is given by is equal to 4.44 flux density into core area into frequency into turns. Right? So E is proportional to A, area of the core. So I write E2 by E1 equal to AC2 by AC1. Similarly, AC2 is equal to 4 times AC1 since the linear dimensions are 2 times. So E2 by E1 equal to 4. Now the kVA is proportional to E into I. So kVA 2 by kVA 1 equal to E2 by E1 into I2 by I1. So that is equal to 4 into 4 equal to 16 times. Okay, okay, we'll go to the next question. Here 2014 one more question. For a specified voltage and frequency, if the equivalent radius of the core of transformer is reduced by half, they're asking us the factor by which the number of turns in primary should change to maintain the same no load current. Generally, flux density in core cross section area is given by number of turns by reluctance. So BM1 AC1 equal to N1, current is same, right? So the no load current is current which is not magnetizing current. So let's say it is IR by reluctance, initial reluctance is R1. Similarly, I can write BM2 AC2 equal to N2 IM is same because the no load current is same. They have specified. Whereas the reluctance R2. Since the radius of core is reduced by half, what happens is AC2 becomes AC1 by 4. Similarly, R2 reluctance becomes 4 times R1. So if I substitute here AC2 and R2 and equate these two expressions, I can write BM1 N2 equal to BM2 N1. Let's say this is one equation. Okay. And we know that from the induced EMF of transformer, we can write E is equal to 4.44 frequency, number of turns, density into cross section area. So I can write E1 equal to 4.44, frequency is same, number of turns N1 into BM1 AC1. Similarly, E2 equal to 4.44, frequency same, number of turns N2. This is BM2 into AC2, 2 into AC2, right? AC2 equal to AC1 by 4. So substituting AC2 equal to AC1 by 4 and equating these two expressions, we will get N1 BM1 equal to N2 BM2. So this is equation. So now if we equate these two, 1 and 2, we'll be getting N1 equal to 2 times N2. Sorry guys, N1 equal to N2 by 2, because BM1 I can write as N1 BM2 N1 by N2, right? So this BM2 cancel. So N1 square equal to N2 square by 4, N1 equal to N2 by 4. Okay, we'll go to the next topic. So we are continuing the basics of transformer. So earlier we have seen the phasor diagram of a transformer on no load. So now we'll talk about phasor diagram of transformer. That is the ideal transformer. So here we will be considering practical transformer, same on no load condition. Let me draw the star diagram first. Okay. So earlier we have seen the phasor diagram of transformer looks something like this. We have primary voltage V1, this is the flux, the V1 equal to minus E1. According to Lenz's law, we'll be having E1 and E2 here, right? This is 90 degrees. This is 90, this is 90. This is a no load condition. Uh, Means for ideal transformer. If you take practical transformer will draw some finite amount of current. To actually draw, let's say that current we call it as no load current. And this no load current actually it's a combination or sum of two components. One is I mu, other one is IW. So this component is called magnetizing current, which is needed to supply the working flux in a core. IW is the active component current, which is required to supply the iron losses. So this current is called reactive component of I naught. This is called active component of I naught. And this current is generally around 4 to 5 percentage of full load current. And this current is around 1 to 2 percentage of full load current. Okay. So I naught is divided into two components. So this is I mu, which lies in phase along the flux, and this is IW. And the resultant of these two current gives us the no load current I naught, which lags the supply voltage by a angle called no load angle. So if you take transformer, so I naught vector sum IW bar plus I mu bar. So if you take, okay, we'll go further ahead. Okay, so the vector diagram of ideal transformer at no load, considering finite core permeability and core loss, is shown here. Generally, the transformer is a constant flux device. So there is no change in transformer core flux from no load to full load. And moreover, in a transformer, primary ampere turns are always equal to secondary ampere turns. That is N1 I1 equal to N2 I2. So this is what I have explained in the earlier slide. Okay, we'll go to the next slide. So here we have one previous year period question. Let me solve. So the low voltage winding of a 400 by 230 volts single phase 50H transformer is to be connected to 25H. Means, so the transformer is designed for 50H, but they are trying to connect to 25H. Then they're asking us the supply voltage should be. We know that transformer is a constant flux device. And earlier we have seen the flux density in a transformer is proportional to ratio of V by F. So since the transformer is a constant flux device, the V max should always be constant. So V1 by F1 equal to V2 by F2, right? So the initially the low voltage, so it is 230 volts by frequency is 50 Hz. It is connected to 25 Hz supply. We have to find the supply voltage X. So X equal to 25 into 230 by 50. So that is 115 volt. So if the low voltage winding of transformer earlier is connected to 230 volt to 50 Hz, so for the frequency in a transformer to be constant, this low voltage winding has to be connected to 150 volts 25 Hz supply. Okay, we'll go to the next slide. So earlier we have seen the diagram of a transformer and no load condition. Considering a transformer has finite permeability and iron losses are present. So now let us consider the vector diagram of a transformer. If there is a load connected on the secondary winding of the transformer. So for ideal transformer, this is flux. Supply voltage V1 equal to minus E1. This is E1, E2. Ideal, right? But for a practical transformer, it draws some no load current I naught to supply iron losses as well as to create working flux. So earlier we have seen transformer primary is connected to supply, the secondary is open circuited. And what I am doing is I am connecting a load to the secondary winding. Okay. So when you connect the load to the secondary winding flows. Let's say I, and let's say load is a lagging type of a load. So what happens? Current I2 lags E2 by an angle theta 2. So what happens is generally the transformer is a constant device. So whenever the current load is connected, this current flows. And due to this flow of current, it will create flux which will oppose the net flux in a transformer, due to which the net flux will decrease. To avoid this, what happens is transformer additional current, uh, will draw additional current which is excess of I naught, in addition to I naught. So that we call it as load component of secondary current before to primary. Okay, so if I2, if you take it the other side, this is called load component current to primary, that is I1 dash. If you take the resultant of these two currents, so that current is called the primary current. That is a current flowing through the transformer. And theta 1 is the primary angle. Generally, no load current I naught dash is around 5% of full load current. So we know that I1 equal to primary current I naught dash plus I1 dash. So this is the second current primary. Generally, no load current is around 5% of full load current. So you can neglect this. In that case, I can write I1 is approximately equal to I1 dash. Right? If you multiply with number of turns N1 and N2, so the transformer MV on primary side is equal to transformer MV on secondary side. Okay, let's go to the next slide. So this is what I have discussed in the earlier slide. Here we have a better picture for the vector diagram. So here is one previous year gate question. A voltage V equal to 400 sine 314.16 T is applied to a single phase transformer on no load condition. If the no load current transformer is 2 sine 314.16 T minus 85 degrees, then magnetic branch impedance will be approximately. Generally, on no load condition, the equivalent circuit of transformer is given by sector is open circuited, right? So we don't have any load. So only we have primary, which has only two shunt components. One is R naught. This is component which represents the iron loss. Then we have X naught. This component represents the current which is required to create working in the transformer, that is I mu. So this is the supply voltage. This is the no load current I naught. They have given us the supply voltage V, that is I can write 400. This is the peak value. Okay, so RMS value if I write 400 by root 2 and angle 0 degree. Similarly, I can write I naught equal to 2 by root 2 and angle minus 85 degrees. Now the impedance this Z naught is nothing but the ratio of V naught by I naught. So that is 400 by root 2 angle 0 degrees by 2 by root 2 angle minus 85 degrees. So if I solve this, I'll be getting 200 angle 85 degrees. Okay, let's go to the next slide. So we are drawing the equivalent circuit of a transformer. Till now we have seen the phasor diagram of a transformer. So first we have seen ideal, then we have seen the practical transformer under no load, then we have seen the practical transformer under load conditions. So using these phasor diagrams, now we are going to draw the equivalent circuit of a transformer under load condition. Okay. So generally transformer has winding, right? We have primary winding and secondary winding. So this winding will has some resistance, right? Because of this resistance, what happens is we'll be having copper losses. So these copper losses are represented by resistor in a transformer equivalent circuit. Similarly, we have one more term called leakage flux. Leakage flux is the flux which links only one winding of a transformer. So if it links both the windings, then it is called mutual or useful flux. And this leakage flux is proportional to the load actually. Hence, it is called as a variable flux. And this leakage flux is represented by a reactance in the transformer equivalent circuit. And what happens if you have a high leakage flux? Because will result in poor voltage regulation. There will be a drop across this reactance, and also transformer capacity will also be reduced. So the leakage flux is modeled as an inductor in the transformer equivalent circuit. So this is what I have explained. Okay, yeah. Uh, said. So on transformer, no load condition, we have V1 here. This is a flag. That is for ideal transformer, but for a practical transformer, we will be having core loss component IW and the magnetizing component. The summation of these two gives us the no load current. Now, when the transformer is under loaded condition, let's say the transformer secondary load winding is connected to a lagging load. So the current I2 lags E2 by an angle. And if you refer I2 to primary side, we'll be hitting I1 dash. And the equivalent of I0 and I1 dash is the primary current I1. Now, if you see here, transformer has primary winding as well as the secondary winding. So this shunt component is used to represent IW as well as IM. So you want to see the voltage across the shunt component is E1. So E1 is equal to V plus R1 I1 plus J times I1 X1, right? So this is V1, E1, right? E1 in the direction of I1 will be getting I1 R1. Okay, if you take V1, that will be I1 X1. The opposite gives us the 90 degrees to current gives us the I1 X1. So the V1 equal to minus E1. Actually, this minus sign is due to the lens law. Okay. So minus E1 plus E1 plus I1 R1 plus I1 X1. Similarly, B2, that is terminal voltage here. V2 equal to E2 equal to V2 plus. So V2 plus I2 R2 plus I2 X2 gives us the E2. Now there is one more topic called referring. Actually, to obtain the transformer equivalent circuit, what we will do is generally we'll transfer this secondary winding impedances to primary side. So by using the concept of referring. So according to the concept of referring, if you want to transfer this resistance secondary side to the primary side, the copper losses before transferring, that is I2 square R2 dash equal to copper losses after transferring, that is I1 square. R1 dash is a resistance, secondary winding resistance referred to the primary. So I can write R2 dash equal to R2 by K square. K is a transformation ratio. Earlier we have seen. So similarly, we can write X2 dash equal to X2 by K square. Let's go to the next slide. So this is what I have explained, the concept of referring. The transformer consists of two electrical circuits, hence to combine these two circuits into one, we use the concept of referring. So the condition for referring resistance is copper losses before referring should be equal to copper losses after referring. That's how we got the R1 dash equal to K2 times R1. Sorry, K2 square, it's not K2. Okay. K2 square.
Suppose earlier we have seen the transformer has primary winding resistance, reactance, there is shunt branch. Similarly, we have secondary winding resistance, reactance, and then load, right? R2, X2, R1, X1. Suppose if you want to transfer this R2, X2 to the other side, so how does it look? First, actually, they will move the shunt branch parameters to the primary side because the current taken by the shunt branch is very less, around 5% of the no load current. So I can move this to the primary side. Then I have R1, X1, and then I have R2, X2, right? Now this R2, X2 I am transferring to the other side. So that is R2 dash, that is equal to R2 by K square. Similarly, X2 dash equal to X2 by K square. So the equivalent circuit will look something like this. We have R naught, X naught, and then we have the resistance and reactance. This is the load. So this resistance is R01. This reactance is X01. So R01 is a summation of R1 plus R2 dash. Similarly, X01 is a summation of X1 plus X2 dash. So there is other way also. We can refer this primary resistance to secondary side also. So then the circuit will look something like this. We have the load here. There is a supply voltage. This is called R02 and this is called X02. So similar R02 equal to R2 plus R1 dash. X02 equal to X2 plus X1 dash. Yeah. So this is one approximate equivalent circuit. Let's say we call it as first approximate equivalent circuit. This is called the second approximate equivalent circuit. So in a first approximate equivalent circuit, we are moving the shunt branch to the further. So because of which what happens is iron losses will get overestimated and no load primary leakage drops are neglected and no load primary copper losses are also neglected. And this type of equivalent circuit is used to find the transformer efficiency. In the second approximate equivalent circuit, iron losses are neglected. We are not considering the shunt branch at all. And this type of equivalent circuit is used to find out the transformer voltage regulation. Okay, guys, we'll go to the next slide. So this is what I have discussed here in the earlier slide. Here we have a better picture. So this is the first approximate equivalent circuit and this is the second approximate equivalent circuit. So let's solve some previous year questions. If an ideal transformer has an inductive load element port 2 here as shown in figure, they're asking us the equivalent inductance referred to the primary side on the port 1. We know that let's say this is similar, let's we call it as x2, similar to nothing but similar to x2, right? What we have seen earlier. So if you want to refer x2 to the primary, it will become x2 dash, which is equal to x2 by k square. K is a transformation ratio and k is given by number of turns on secondary by number of turns on primary. So the number of turns on secondary is 1, number of turns on primary is n. So I can write x2 dash equal to x2 by k square. K square is 1 by n whole square. So that is n square times x2 or n square times L. Okay, L2.
We'll go to the next question. So GATE 2014 1 mark question. Assuming an ideal transformer, the Thevenin equivalent voltage and impedance as seen from the terminals X, Y for the circuit in figure R. So here we have primary side resistance. So this is similar to our R1. And if we want to transfer it to secondary side, it becomes R1 dash, which is equal to R1 into K square. So K is a transformation ratio, that is N2 by N1. So that is 2 by 1. So R1 dash equal to R1, that is 1 ohm into K square is 4. So that is equal to 4 ohms. Okay, we'll go to the next question. Go GATE 2010 question. A single phase transformer has a turns ratio of 1:2 and is connected to a purely resistive load as shown in the figure. The magnetizing current drawn is 1 amps. So here it is 1 amp and the second current is 1 amp. The core losses are and leakage reactance are neglected. They're asking us to find out primary current. We know that in a transformer, primary MVA equal to secondary MVA. N1 I1 equal to N2 I2. So I can write I1 equal to N2 by N1 into I2. So that is 2 by 1 into 1 amp. So that is 2 amps. That is I1. Now we know that the I1 total resultant current is a summation of no load current vector sum plus I1 dash. Actually, this is I1 dash. So I can write I1 equal to square root of. Why? Because it is a vector sum. 2 square plus no load current is 1 square. So that is root 5. That is 2.24 amps. Just give me a minute, guys. Okay, guys, let's go to the next topic. Transformer losses. Transformer losses are classified into two types. One is the major losses, the other one is the minor losses. These major losses are further classified into two types. One is copper loss, the other one is iron loss. These minor losses are also classified into two types. One is stray load loss, the other one is dielectric loss. And copper losses, total copper losses in a transformer is given by primary current square into primary winding resistance plus secondary winding current square into secondary winding resistance. And copper losses are directly proportional to the load. So the other way to write copper losses is we can write I1 square into R01, or we can also write I2 square into R02. So we have seen the expressions for R01 and R02 in the earlier slide. And here one formula is copper loss at X fraction of full load equal to square times copper loss at full load. Copper loss at half full load equal to 1 by 4 times copper loss at full load. And next we have iron losses. These iron losses are also classified into two types. One is hysteresis loss, the other one is the eddy current loss. The expression for hysteresis loss is given by eta V max to the power 1.6 F into V. And similarly for eddy current losses, it is given by K into B max to the power square to F square into T square. This is thickness. So let's go to the next slide. So this is what we have discussed in the earlier slide. Okay. We have seen that the hysteresis losses WH is proportional to B max to the power 1.6 into N. So now if in a transformer, if the ratio of E by F is constant, which means B max is constant, right? So we'll take two conditions. V by F constant, V by F not constant. So if we substitute V by F here, what happens? It is proportional to V by F whole to the power 1.6 into F. If V by F is constant, then WH is proportional to F. If V by F is not constant, then WH is proportional to V to the power 1.6 and F to the power minus 0.6. Similarly, we have eddy current losses, which is proportional to
V max square F square. So here also we'll take two queries, V by F constant and V by F not constant. When we have V by F constant, which means B max is constant, so W is proportional to F square. And B max is constant, then substitute V by F in B max. Then we'll be getting W hysteresis, eddy current loss is proportional to V square. We'll go to the next slide where we'll be solving few previous year questions. So this is what we have seen in the earlier slide. Single phase 400 volts 50 H transformer has an iron loss of 5000 watts. The condition when operated at 200 volts 25 H, the iron losses is 2000 watts. When operated at 416 volts 52 H. They are asking us to find out the value of hysteresis loss divided by eddy current loss. We know that here if you see the ratio of V by M, V1 by F1 equal to 200 by 25. So that is 8. V2 by F2 equal to 416 by 52. That is also 8. So V1 by F1 equal to V2 by F2, which means Vmax is constant, right? So when Bmax is constant, I can write hysteresis losses proportional to or hysteresis losses can be given as some constant kh into frequency into b to the power 1 point. Similarly, eddy current losses is given by
Ke F square B square. Now take the first case when V1 by F1 equal to 100 by 25. So I can write WH plus WE equal to KH, frequency is 50, sorry, it's 25H, right? 25H e to the power 1.6 plus KE 25 square B square, that is equal to W H plus WE is nothing but WI, that is a total iron loss, that is equal to 5000 watts. This is one equation, and the second equation corresponds to V2 by F2. So that is equal to KH 52 B to the power 1.6 plus KE 52 square B square, that is equal to WI, that is equal to 2000 watts. This corresponds to equation 2. If we solve equation 1 and equation 2, we'll be having KH B to the power 1.6 equal to 60, KE B square equal to 20 by 25. Now what they're asking the ratio of hysteresis losses divided by eddy current losses. That is KH F F. Okay, hysteresis losses by eddy current losses at 52 degrees centigrade, at 52 H. We given as KH 52 e to the power 1.6 by KE B square 52 square. If you solve this expression, you will be getting 1.44. We'll go to the next question. The next topic is transformer testing. So here we'll be discussing up two transformer tests. One is open circuit test. The other one is the short circuit test. So let's start with the open circuit test. Open circuit test. Open circuit test is also called as load test. So what are the objectives of this open circuit test or no load test? To find out the constant losses. So that is first objective. The second objective is to find out the shunt branch parameters of transformer equivalent circuit, that is R0 and X0. And the third objective is to separate the iron losses into hysteresis and eddy current losses. So let me draw the circuit diagram. So this is the source on primary. We'll be having voltmeter and then ammeter. For that we have this is wattmeter. This is connected to primary winding of a transformer. Generally, OC test is done on LV side, which HV side as open circuit. HV side is open circuit. And these wattmeters are of two types, LPF wattmeters and UPF wattmeters, low power factor and upper power factor. So the low power factor means less than 0.5 pi. UPF means greater than 0.5 pi. Okay. So under no load condition, the current drawn by the transformer primary winding is called no load current I naught. I naught, right? So the ammeter reads I naught and wattmeter measures the no load losses, which can be given as supply voltage into no load current into cos theta naught, no load power factor. So from this, the no load power factor cos theta naught can be given as wattmeter by V1 into I naught. We know that the input power equal to output plus losses, right? So here we don't have any output because it is open circuited. So the input power equal to losses of the transformer under no load condition, that is iron losses. Okay, so once we got the cos theta, the active component current IW can be given as I naught cos theta naught. Similarly, the reactive component I mu is given by I naught sin theta naught. So we know that the transformer equivalent circuit under no load condition looks like this. This is R naught, this is X naught, this is the supply voltage V, R naught, X naught. So this is the I naught, this is IW, this is I mu. So we know got IW and I mu. So the expression for R naught is V1 by IW. Similarly for X naught is V1 by I mu. So we are able to find out the constant losses as well as the shunt branch parameters. And the next we'll go to the short circuit test. This is what we have discussed in the earlier slide. Next one is a short circuit test. Short circuit test is performed on the HV side of the transformer, keeping LV side shorted. The objective of the short circuit test is to find out the variable losses and also to find out the series branch parameters of the transformer equivalent circuit. The short circuit test is generally conducted at reduced voltage and at rated frequency. So here we need the wattmeter which is of type UPF type. In the open circuit test we need a wattmeter of type LPF. Let me draw the test circuit. We have a supply voltage V, then we have auto transformer, and then we are applying the reduced voltage on the HV side of a transformer. We have an ammeter, then we have the wattmeter. So this is the wattmeter which is of type UPF.
Then we have the HV winding. Here we have the LV winding. LV winding which is shorted. So we know that input equal to output plus losses. Output is shorted, right? So V is 0. So the output power is 0. So the input power equal to losses. That is equal to copper losses. That is, let's say the current flowing is short circuit. So S square into R01. So this is nothing but the wattmeter reading. From this we can get R01, the total resistance of the transformer equal to WSC by ISC square. ISC can be obtained from the ammeter reading. Okay. So once we have ISC, we can also get Z01 by VSC, reduced voltage, this one by the ammeter current. So this gives us Z0. Once we have R01 and Z01, the X01 can be given as root over Z01 square minus R01 square. So we are able to find out the series branch parameters of the transformer as well as the variable losses. And one more point is the percentage resistance is equal to percentage full load copper losses for a transformer. Okay. Then we'll go to the next question. So this is what we have seen in the earlier slide. So this is a GATE 2008 question. Let me. So there, it is desired to measure the parameters of a 230 volts, 115 volts, 22 kVA single transformer. So these are the wattmeters which are available in the laboratory. They are asking us out of these four wattmeters, which of them can be used in open circuit test and short circuit test. We know that for open circuit test we need LPF. For short circuit we need UPF or HPF. Right? So open circuit we need any one of these. Short circuit we need any one of these. But in open circuit test, generally the ammeter reads the no load current. General no load current is very small. So if you take the ammeter which has low range, it reads that lower value accurately. So this is preferred for open circuit test, and similarly for HPF, we need W3. Okay, let's go to the next question.
Okay, this question is related to transformer efficiency. So let's discuss the first the topic of transformer efficiency. Then we'll look at these kind of questions. Okay. Generally, the efficiency is given by output by input, right? Similarly, the transformer efficiency in percentage can be given as output power by input power 200. We know that input power is a summation of output power plus losses, right? So the output power can be given as, let's say, E2 is the secondary terminal voltage and I2 is the current flowing, and the angle between them is theta 2. So E2 I2 cos theta 2 by E2 I2 cos theta 2 plus losses. Losses we have variable loss plus constant loss into 100. Now the condition for the maximum transformer efficiency is the variable loss should be equal to the constant losses, which means variable loss, that is copper loss, equal to constant loss, that is iron loss. Then the efficiency of a transformer is maximum. So if you draw the plot, the transformer efficiency with respect to load current, the efficiency increases and it gets maximum at some point. This is a point where the variable losses and the iron losses are equal. And if you draw the same curve for different power factors, different values of theta 2, we have curves like this. So the highest one corresponds to UPF, and the next one corresponds to say zero point 0.8 power factor, and last one corresponds to zero point 0.6 power factor. So in the next slide, I will show the clear picture. So this is what we have discussed in the earlier slide. Here the curves are more clear. Try to solve this question, guys. Sorry guys, I missed one question. So let's try to solve this question first, then I will go to the next one. The efficiency of a 100 kVA transformer is 0.98 at full load as well as at half load. For this transformer at full load, the copper losses or find the relation between copper loss and core loss. The transformer efficiency is given by kVA out into power factor by kVA out into power factor plus iron loss plus copper loss, right? Now let's say the power factor is unity. So efficiency full load equal to 100 kVA into 1 by 100 into 1 plus Wi plus WCU. This is equation 1. So when the efficiency half load equal to 50 kVA into 1 by half load, right? So it's 1 by 2 times that of 100 kVA. So 50 into 1 plus iron losses remains the same, whereas and because if they don't vary with respect to the load, that's why they are called constant losses. Whereas the copper losses becomes, we know earlier we have seen, right? The copper losses at x fraction of load equal to x square times full load. So it is 1 by 4 times WCU. So that is equation 2. So when we solve this equation 1 and 2, we'll be getting copper loss equal to 2 times iron loss. Okay, we'll go to the next question. So here 2003 one mark question. A single phase transformer has a maximum efficiency of 90% at full load and unity power factor. Efficiency at half full load and same power factor is. So under maximum efficiency condition, we know that copper losses are equal to iron losses. Now efficiency full load can be given as, considering power factor as unity, kVA full load by kVA full load plus 2 times X iron losses. So that is, they have given it is equal to 90%, that is 0.9. So if we solve this equation, we can get Wi equal to 1 by 18 times kVA full load. Next, efficiency half full load can be given as half into kVA full load by half kVA full load plus iron losses plus 1 by 4 times copper loss. So that they have given us, no, that we have to find out. So, but we know the expression iron loss is equal to half times kVA full load. So in case of kVA full load, if I write 18 Wi. We also know that copper loss full load equal to iron loss full load. So from this I can write half kVA full load by half kVA full load plus 5 by 4 times Wi. So if I use this expression here and solve, I will be getting around 87.8 percentage. The next one is a GATE 2006 2 marks question. A 300 kVA transformer has 95 percentage efficiency, full load 0.8 power factor lagging, 96 percentage efficiency at half load unity power factor. They're asking us to find out the iron losses in kilowatt under full load operation. We know that the efficiency full load can be given as 300 into 10 cube because it's kVA, power factor is into 0.8 by 300 into 10 cube into 0.8 plus iron loss plus copper loss. That they have given us 0.95 percentage. They also have given us efficiency half full load equal to half into 300 into 10 cube into 1 by half into 300 into 10 cube into 1. But half full load iron losses will be same. Copper loss is 1 by 4 times copper loss. So that is 0.96. If we solve these two equations, we can get iron loss equal to 4.1 kilowatt and copper loss equal to 8.5 kilowatt. Okay, let's go to the next question. Actually, this is a continuation of the earlier question. So they're asking us to find out maximum efficiency at unity power factor load. So we know that for a maximum efficiency, general, sorry, first we have to find out the percentage of full load at which max efficiency occurs, right? So that is given by square root of Wi by WCU. So that is equal to 0.696. Now the percentage eta max equal to x time, right? This is a fraction. So 0.96 into 300 into 10 cube. Then actual maximum efficiency is possible at unity power factor by 0.696 into 300 into 10 cube into 1 plus iron losses plus copper losses, that is 4.1 kilowatt plus, and the copper losses becomes 0.696 square times that of earlier copper losses, that is 0.48 into 8.5 kilowatt into 100. So if you solve this expression, we will be getting 96.2 percentage. Okay, let's go to the next question. A transformer has an iron loss of 4.5 kilowatt and full load copper loss of 50 kilowatt. They're asking us to find out the percentage load at which transformer is expected to have maximum efficiencies. So we have a formula that the efficiency is maximum at x fraction of full load, and that x is given by square root of iron loss by copper loss. So that is equal to square root of 40.5 by 50. So that is 0.9. So maximum efficiency occurs at 0.9 times of full load. That is 90 percentage of full load. We'll go to the next topic. So generally the transformers are of two types. One is power transformer. The other one is distribution transformers. So what are the difference? The power transformers are used in transmission lines, whereas distribution transformers are used at the distribution level, that is less than 11 kV, 33 kV I can say. The transmission lines greater than 33 kV, distribution level is less than or equal to 33 kV. And here in power transformer, iron losses takes place throughout the day. Here all iron losses takes place throughout the day, whereas the copper losses depends upon the load connected on the transformer. So this is subjected to less load fluctuation because at the transmission level. Since it is at the distribution level where the individual loads are connected, single phase loads. So this is subjected to more load fluctuations. And here while designing, the copper losses are tried to be kept to minimum, whereas here while designing the iron losses are tried to be kept minimum because the primary is always excited, whereas the secondary depends upon the load profile. Okay, let's go to the next topic, which is voltage regulation. Voltage regulation is defined as change in terminal voltage from no load to full load expressed as a fraction of no load secondary terminal voltage. Suppose let me draw the transformer equivalent circuit referred to the secondary side. So here we have the load. This is the secondary voltage, no load. This is R02, X02. This is the load. Let's say this voltage is V2. Now the percentage voltage regulation is defined as E2 minus V2 by E2 into 100. So this can also be given as I2R02 cos theta 2 plus or minus I2X02 sin theta 2 by E2 into 100. So this can also be further written as percentage voltage regulation equal to percentage resistance into cos theta 2 plus or minus percentage reactance into sin theta 2. So theta 2 is a load power factor angle, and positive sign is used when lagging type of load is used on the secondary side. Negative sign is used when leading type of load is used. And here also voltage regulation at X fraction of full load equal to X times full load voltage regulation. Okay, let's go to the next slide. So this is what we have discussed in the earlier slide. Now the condition for a earlier we have seen the expression for voltage regulation as percentage voltage regulation equal to percentage R cos theta 2 plus or minus percentage X sin theta. So the voltage regulation is maximum and the sign is positive. That is for lagging type of load. And it's minimum for leading type of load. The condition for maximum regulation is given by theta 2 equal to tan inverse x02 by r02. And it occurs at lagging power factor of the load. And the value of maximum voltage regulation equal to percentage impedance Z. That is percentage R square plus percentage X. And the condition for zero voltage regulation is given by theta 2 equal to tan inverse R02 by X02 and it occurs at leading power factor O. Negative voltage regulation is possible only for capacitive loads. Now we'll go to the next slide. So this is what we have seen in the earlier slide. We'll solve some previous year questions. So it's a grade 2018 one mark question. So what they have given a single phase 100 kVA 1000 volt by 100 volt 50H transformer has a voltage drop of 5% across its series impedance at full load. Of its 3% is due to resistance. Percentage regulation of the transformer at full load with 0.8 lagging power factor is. Know that the percentage voltage regulation equal to percentage R
cos theta 2 plus or minus percentage x sin theta 2, but I have given it as lagging power factor, so it is positive. Power factor means cos theta 2, that is 0.8. The resistance is 3%, impedance is 5%. So the x can be given as percentage x equal to root over percentage r square, that is 3% square, z square minus 3% square. So that I can write as 4%. So 3 into 0.8 plus 4 into 0.6. This gives us the percentage voltage regulation.
We will go to the next question. So here 2019 1 mark question. A 5 kVA 500 by 100 volt single phase transformer has a secondary terminal voltage of 95 volts when loaded. The regulation of the transformer is. So when it is loaded, the voltage is 95 volts and the secondary terminal voltage after no load condition is 100 volts. We know that percentage voltage regulation is given by E2 minus V2 by E2 into 100, right? So E2 is the no load voltage, that is 100 minus 95 by 100 into 100. So this is 5 percentage. So percentage voltage regulation equal to 5 percentage. Okay guys, that's all for today's class, and in the next class we'll cover the remaining topics in transformers such as auto transformer and the three-phase transformers. Thank you all.